All right, let's look at this week's agenda. It's last week for instruction for this quarter. Next week we'll have our finals week. For this week, we'll go over chapter 7. No homework, no quiz for this week, right? And then there will still be final project demo. And yeah, make sure you do that during lab sessions this week. Even if you're in the different lab session, for example, if you're in Thursday lab section and you want to do the demo today, you're welcome to. We have our Tuesday lab section from 3 to 6 today. So feel free to stop by if you are ready to demo your lab today or your final project today. Okay.
We have until Friday to do it though, right? Like to schedule an appointment?
That's correct, yes. So if you can't do it during lab sections or lab sessions, I should say, yeah, if you need more time, then Friday by 5 p.m. will be the deadline for demoing the project. Okay. So make sure you let me know if you want to do it beyond the lab sessions for this week. Okay. I'll be more than happy to set up the time for you to do the demo. All right. Any questions? Any other questions? No? All right. And then I have a couple of announcements for next week, since we have our final exam next week, a week from today. Please verify, double check and verify if I'm making a mistake here, but I believe our final exam is going to be next week, Tuesday. So again, a week from today. It's going to be from 2 to 4, so 2-hour final, not 3 hours, okay, 2 hours. Yeah, Tuesday of next week, online, synchronous, just like the midterm exam. And then please use the same Zoom link as you've been using for the lectures, right? So it's going to be the same link. Not comprehensive. It's going to cover chapters 4, 7, and 8. Let me double check on that one. Chapters 4, 7, and 8. Is that right? Let's see. 4, 7, and 8. Yes. Okay. An open book, open notes, and then I'll provide even end of chapter answers to end of chapter problems, even numbered problems on Canvas. Right. And then finals week office hours will be different from the regularly scheduled office hours for the quarter. Like, since the final is on Tuesday, I also have another final on the same day. So both finals will be on Tuesday for me. Therefore, I've decided to hold my office hours on Monday. Right. So next week Monday will be from noon to 5. Okay. And there's the link for the office hours next week. I'll send it out. I'm also posted on Canvas. I'll send it out by email, this link right there, and also post it on Canvas, so you know where to log in for office hours next week. Any questions on these? Any of these? No? All right. If not, let us start with chapter 7. So we're done with chapter 8, I believe, right? Yes. I keep forgetting the chapter numbers. What's the inverted chapter? Chapter 8, isn't it? Yes.
Yeah.
Okay. Yeah, we're done with chapter 8. So now we're going to go into chapter 7. Now, the reason why I picked chapter 7, I still have actually 3 more chapters, but I'm going to pick the most relevant chapter for you to learn from this class, which will be chapter 7. To me, this is most relevant because I like this chapter because it also gives you, I mean, before I go there, sorry, what you've been learning so far are the benefits, right? Mostly or mainly the benefits, all the great things that power electronics has offered for us, right? But it's also good for us, for you, to know the dark side of power electronics, if you will. What are the disadvantages, right? Problems, issues related to power electronics, right? So we need to know both, right? Benefits as well as the technical problems that power electronics cause, right? So hopefully by knowing the problems or the issues that power electronics gives us, you as future generation, and if you're interested in power electronics, hopefully you can take a look at these issues, and hopefully you can attempt to solve at least these issues, right? Maybe you can find out innovative way or creative way of solving these technical issues, right, related to power electronics. Okay, so not just taking advantage of power electronics, but also understanding the technical issues, problems, challenges in power electronics, with the hope that someday if you run if you come across the issues, then hopefully you'll at least you're familiar with the issue, you've heard it before, and hopefully you'll be able to help us solve the issues. Okay, so the main technical, one of the major challenges or problems with power electronics is the inherently the waveforms that we produce in power electronics are caused by switching, right? So one of the major issues would be noise, right? And noise could be translated into different things, but in terms of AC power, this noise translates into what we call harmonics, right? And harmonics is going to be harmonics defined to be actually part of a bigger issue in power systems called power quality, right? Now, so this problem, even though it is related to AC power, right, to me it's still important for you, even if you, let's say you are only interested in DC to DC converters, right? And don't forget, right, that majority of the power that we have in this world, comes from AC power, right? So yes, even though you are dealing with DC to DC converters, that or you're designing DC to DC converters, but possibility of you in or the likelihood for you to use AC power is what I feel like it's important for you to also learn a little bit about the AC side of power electronics, right? Especially related to the issues related to or caused by power electronics, right? And also it's good for you to learn more about the AC side of power electronics, because power electronics is not just being used for DC to DC, but also for other type of conversion, right? As you already know, it's been used for AC to DC, DC to DC, DC to AC, AC to AC, right? And yeah, if you work for companies like General Atomics, for example, right, or microturbine generators, for example, then you'll be dealing with, or you'll be looking at issues with AC side of power electronics, right? So I think it'll make you more what do you call it? More, what's the word I'm looking for? More well-rounded, I guess, right? In terms of knowledge, students with with additional background in power quality, for AC power. Okay, so that's just a little bit of a background on why I feel like this chapter is important for us to go over. Okay, any questions before I start? All right. So what is power quality? Right? Again, keep in mind that power quality is a specific problem that utility system or AC power side of the electrical system typically encountered, not just from power electronics, but for from other sources, right? So what is power quality to begin with? How is it being defined? Power quality is defined to be any power problem manifested in voltage, current, or frequency deviations resulting in failure or misoperation of equipment, right? That's the definition of it. So any problem, right? Any distortion in voltage, current, frequency deviations in any of those, that would correspond to what they call power quality problem. Why concern about power quality? Historically, power quality problem is not new. It was recognized in 1920s and early 1930s. A distortion on voltage and current waveforms in the power systems were observed back then. And the major concerns were the effect on electric machines, telephone interference due to this distortion in voltage and current waveform. So it affects through coupling, right? Capacitive coupling, inductive coupling, in terms of noise, right? Interfering communication lines. Nowadays, there is a growing concern on PQ problems, and PQ stands for power quality. PQ problems due to the following reasons. Load equipment is more sensitive to PQ variations than equipment in the past. Many new load devices contain microprocessor-based controls and power electronic devices that are sensitive to many types of disturbances. And I've actually ran this experiment before a long time ago in our power electronics lab. I don't know if you're familiar with PLCs, programmable logic controllers. Unfortunately, we don't have face-to-face lab this year, but I was very fortunate to receive a big donation from Schneider Electric. They donated PLCs and high-end PLCs, and because of that, I'm developing a new lab for a future power class called industrial automation, industrial power controls and automation. And we've had the setups, I would say 75% done in one of the lab spaces we have in building 20. And these PLCs they're being used a lot in industries, for automation, for controls, manufacturing lines. And these PLCs, these are sensitive load. And I ran one experiment a long time ago, not using the same PLCs, but similar. I'm running two things at the same time, like in parallel, basically, two loads in parallel. One is adjustable speed drives, which is known to generate harmonics, and adjustable speed drives by itself is a power electronics converter, right? It is an equipment to be able to control the speed of induction motor. Also, an equipment that is commonly used, widely used nowadays, adjustable speed drives. So if you hear the term ASDs or VFDs, those are adjustable speed drives, okay? ASD stands for adjustable speed drives. VFD stands for variable frequency drives, but they're the same, basically the same equipment to control induction motor. And they use it a lot in California, especially for irrigation pumps, right? For HVAC, for fans and things like that. So anyhow, so we have this device that is commonly used these days called adjustable speed drives. At the same time, we also have these new controllers that is also widely used these days, for automation, manufacturing line and things like that, called PLCs. Now, PLCs are very sensitive load, right? This is what I'm trying to get at. PLCs, they are very sensitive load in a way that the input the input voltage to this PLC have to be very tight, that if it fluctuates a lot, has transients, introduce transients into these PLCs, then the PLC would just shut off, right? So I proved that by running an experiment a long time ago in our electronics lab. I have the two running in parallel. I have an adjustable speed drives in the lab as well as PLC, and I turned on both actually. I turned on both adjustable. Actually, no, I turned on PLC first. I turned on PLC first, right? And then PLC is, it's working just fine. And then as soon as I turned on adjustable speed drives, and they're connected to the same secondary side of transformer, sure enough, the PLC shuts off. It's really interesting to see that as soon as I turn on the adjustable speed drives, PLC shuts off. Right? And that happens because adjustable speed drives requires current that is non-sinusoidal from the transformer, and that current non-sinusoidal current translate into distorted voltage, right? Because they're connected to the same secondary side of the transformer, and that same distorted voltage is being seen by the PLC, and that's the reason why that PLC was not happy and it just shuts off, right? So keep in mind that nowadays we have more and more sensitive loads, microprocessors, same way, right? PLCs, microprocessors, those are sensitive loads, and they're not meant to see, distortion in voltage as well as currents, right? And then, so that's the first problem. That's the reason why PQ problem is increasingly important, because we have many loads that are now sensitive to voltage quality as well as current quality, right? The increasing emphasis on overall power system efficiency has resulted in continued growth in power electronics. As you learn from EE411, the main objective of power electronics is to be able to convert energy from one electrical energy from one form to another form in the most efficient manner, right? So everybody's, nowadays, for efficiency, right? So saving energy, basically, right? And that's the reason why more and more power electronics based loads are being used, right? ASDs, I just mentioned that, ballast, switching mode power supply, UPS, that's not United Parcel Services, by the way, that's uninterruptible power supply. And then LED light bulbs, that's a big thing nowadays. All of those smartphones, when you charge them, right? Smartphone charger, wireless charger, those are, power electronic, those are electronic devices that have power electronics interface, right? So more and more power electronics being used nowadays, and that is good on one hand, right? But on the other hand, you'll see that power electronics creates this problem of corrupting the power systems connected to it, right? And then increased awareness of power quality issues by the end user. Utility customers are becoming better informed about such issues and challenging the utilities to improve the quality of power delivered. Direct economic impacts. I just told you about sensitive loads, right? Imagine if we have a manufacturing facility, right, that relies on the operation of these, PLCs, and then we have, let's say, some power quality problem because somebody nearby, is running huge, adjustable speed drives. Right? Imagine what that does to manufacturing line, right? It's going to shut down the PLCs. And this happened before. I'm not going to say where, but when I worked for SDG&E, I was part of this was a long time ago. I worked with Power Quality Group. It was a fun, actually, job, summertime at the time, summer work. And almost like, I don't know if you watch those series, CSI, that's kind of like what we did. We were the CSI of the company. We have any issues, in the field, and we are being sent to look at the issues and investigate what caused the issues, what are the root causes, and how do you solve the problem. But one of the problems that we got called for, there's a big manufacturing line in San Diego, and that manufacturing line had to be shut down because of the power quality problem, right? Some of the PLCs that they use just shut off, right? And they of course will blame they blame the utility company, right, because of that. And so we have to come and actually investigate, and it turned out to be that it's not the utility side that's responsible for that, and it's actually another part of the manufacturing line that is responsible for causing that problem. Anyhow, at the end, we came up with a solution, and some advices, some suggestion on how to fix the problem. And I'm not sure if they actually did that, because I was just there for the summertime, and I left after we wrote some suggestions for the manufacturing company to resolve the problem, right? And so that's a big issue, right? If a manufacturing line shuts down, that's a loss of income, right? Direct economic impacts for the company, right? And then detrimental effects, circuit breakers, these protection devices that we put in power systems, power equipment, they rely on zero crossings. If you picture a sine wave, sinusoidal waveform, right, ideal sine wave, then every sine wave would have in one period 2 zero crossings, right? But if the sine wave is distorted, then it will have more than 2 zero crossings. So imagine if the controller that we rely on, to operate these circuit breakers, they rely on zero crossing phenomenon, right? Zero crossing voltage. Then imagine the controller will probably get confused, right? Quote unquote, right? Get confused because now it's seeing more than 2 zero crossing per cycle. So circuit breakers may trip prematurely because of that, right? Same thing with, for example, digital clocks that relies on, again, zero crossing control. Now it's seeing more than 2 zero crossings, and that would definitely, mess up the controller, and now you're seeing, a faster time from the digital clocks, right? Lights flicker, power factor correction, capacitor blows. These are just some of the technical of the resulting some of the problems resulted from issues created by power electronics, right? So just a couple of interesting graphs to show. I believe this is in Georgia somewhere. Yeah, Georgia Power, they ran a survey to utilities and to their employees, as well as to the public, right, to the customers. And what's interesting to see is that, number one, both agree, right, customer side and utility side agree that majority of power quality problem comes from natural causes, such as lightning, for example. But what they disagree on is this, I believe, yeah, right there. See the utility side, oops, sorry, go ahead. Let me go back here. The customer side, 70% thinks that utility is to be blamed, right? So that's from the customer perception. From utility perception, it's quite the opposite. 25% is the fault of the customers, right? They kind of blame each other because of this. So I thought it was interesting to show, which makes sense. Utility wants to blame the customers, and the customer wants to blame the utility. Right? So I thought that was important to show. Not important, but interesting to show. All right. Power quality problems may arise due to a variety of phenomena called disturbances that occur on time scales ranging from 1 millisecond to steady state. Right? So we have different types of power quality problems. Okay, so this could happen if you are using single-phase AC, three-phase AC for the electrical system that you're designing in the future. Right? Transient problem, long duration voltage variation, short duration voltage variations, voltage imbalance, waveform distortions, voltage fluctuations, power frequency variation. Those are different types of problems caused by, or not caused by, that fall into power quality issues. So briefly, let's go through the different definitions. Right? Transients classified into, so transient problems in power quality refers to impulsive or oscillatory transients. Impulsive transient refers to a sudden, non-power frequency change in the steady state conditions of voltage, current, or both, that is unidirectional. So the key word there is unidirectional, right? Either positive or negative. So the pulse is either positive or negative. Most common cause is lightning. That's here's an example of it right there. Lightning stroke, causing current impulsive transient in the system, in the electrical system, right there. Right? Oscillatory transient refers to a sudden non-power frequency change in the steady state condition of voltage, current, or both that includes positive and negative. Most common cause, capacitor bank energization. Right there, you have oscillation in the system, right? And this is 60 hertz or 50 hertz, most likely 60 hertz waveform, right? It just squeezed together into, I don't know how many seconds. Oh, that's only 6 milliseconds. So sorry, no, this is the high frequency oscillation on the 60 hertz system, right? So you can see that's current. So the amperage fluctuates, right? From big fluctuations and decays, right? And this happens due to the resonance in the system. As soon as you introduce capacitance into the power line. Now, power line is mostly inductive. So what happens if capacitor meets inductor? You learn from this class or also from 212 that they form resonance, right? So LC resonance. So that's what you're seeing there. It's LC resonance, higher frequency resonance, right, in the 60 hertz system. And this is another example of oscillation right there, right? You can see here's the 60 hertz sine wave, but there, when you see spikes right there, that's when we connect power factor correction capacitor, right? So again, if you have a power line that's mostly inductive, and then you have power factor correction, which is capacitor, right, basically, right there. Then as soon as you turn on the capacitor, then you're creating, LC resonance, right? And that's the high frequency. If you zoom in to the sine waves, that's high frequencies, right? High frequency sine wave, higher than 60 hertz. And that frequency is basically 1/2 pi times square root of L of the systems times the capacitance of the power factor correction capacitor. Right? That's what creates this oscillation. And why is this important to know, especially if you're in a utility company or if you are designing AC electrical system for airplanes or UAV, right? Then you have to care about this because that's a spike in this. That's an over voltage, right? Compared to the normal voltage, that could be damaging to the rest of the components in the electrical system, right? So you want to be able to avoid this, right? Okay, and one way to avoid it is by turning on the capacitor at zero crossing, right? Peak of the sine wave, that's the worst case for you to turn on the capacitor, for you to connect a capacitor into a power line. Like that's going to give you the largest energy, right? Largest possible energy to the resonant ringing, right? But if it's zero voltage, then where's that energy coming from, right? If there's no voltage source to supply energy to the LC tank, right? So that's why if you are utilizing power factor correction capacitor, you want to make sure that you look for the zero crossing, right, of the sine wave before you turn on the capacitor, or when you turn on the capacitor. Feel free to interrupt anytime you have any questions, okay? Long durations, voltage variations. This could be over voltage and under voltage. Right? Over voltage is an increase in the RMS of AC voltage greater than 110%. So any voltage fluctuation greater than 110% for a duration of longer than 1 minute, that's called over voltage, right? Right? Under long duration. So long duration means larger than, or not larger, longer than 1 minute. Under voltage is also more than 1 minute, but the voltage is less than 90%. And I've listed the most common causes for over voltage is big load switching off the system. And then for under voltage is the opposite effect, right? You are connecting heavy load to an electrical system that would definitely create some drop in the voltage by Ohm's law. That's what you're going to have, right? Short duration voltage variations. So instead of long duration, now short duration, right? Are caused by fault conditions, energization of large loads, high starting current of induction motor. You learned that in 295 lab, right? That as soon as you turn on, when you turn on AC machine, induction motor, then you're going to be dealing with significant starting current, right? As high as 5 to 8 times normal current, right? So if the nominal rating of the current is 5 amps, then when you start induction machine, the current can go up to about 30 amps or even more. Right?
Professor, just due to the size of the electrical grid, wouldn't just a few an extra 30 amps from just a single machine power energizing at once, assuming that they don't all happen simultaneously, wouldn't it be pretty small compared to all the loads being drawn at that moment?
Yeah, that would depend, right? I think you said it correctly. That would depend on the size of the electrical system, right? If you have a single phase induction motor, like in your house, right, and it's drawing 30 amps quickly, that's going to affect the voltage in your house, right? That's a local electrical system. You know, it's a weak system. But
because the step down transformer near our house has lower voltage and relatively higher current.
That's right, yes. But if you see the effect on the primary side of the distribution transformer, I don't think that will see the effect at all, right? It's because the primary side of the transformer is connected to so many other houses, so it's a bigger electrical system, right? And then same way, if you are running three-phase induction motor, let's say for irrigation pumps, that would really depend on the horsepower of the pump, right? If the pump is tens of horsepower, that's big, right? And so no longer you're dealing with 30 amps, you're dealing with probably hundreds of amps at starting point, right? And that would drop the voltage easily on the distribution line, right? So really depends on the size of the machines and as well as the capacity of the electrical system, right? So hopefully that answers your question.
Yeah, that clears it up.
Right. I don't know, but I've seen it before. I think nowadays it's pretty good. I don't remember where. Maybe when I was in Atascadero, maybe. Anytime I turn on AC, I could kind of see quickly that the lights kind of dim a little bit, right? Quickly. That's coming from the starting current of the motor being used by the air conditioning, right? I don't know if you've seen that before, that the light dims a little bit when you turn on the AC. All right. Interruptions occur when the supply voltage or load current decreases to less than 0.1 per unit. So 0.1 per unit is basically the same as saying 10% of the normal value, right? So if the voltage or load current decreases to less than 10% of the nominal value for a period of time not exceeding 1 minute, that's called interruption, right? That could be caused by system fault, equipment failures, and control malfunctions, right? And then we have this event, I'll call it event called SAGs. So this is, if you look at the level, it's the same as under voltage, right? That I went over earlier, between other voltage is below 0.9, right? But this one specifically between 0.1 and 0.9. So if the voltage goes down to between 0.1 and 0.9, or 10% to 90% of the nominal value for a duration, so this is very specific, for duration for the duration between 0.5 cycles and 1 minute, then we call that voltage sags, right? So something like this, for example, right? So you look at the duration. If it's between 0.5 and 1 minute, and the level is between 0.1 and 0.9 of the nominal value, we call that voltage sags, right? The opposite of that is a voltage swell right there. And what is the, sorry, before I go there, what is the cause of voltage sag? System faults, energization of heavy loads, and then also starting of a large motors. All right. Oh, I forgot to ask. I don't know if you remember this. Why is it that induction machine has large starting current? What did you learn from 295? You learned it there, but let's see if you remember why. Why is it that induction motors at starting requires a lot of current?
Doesn't the rotor need to be spinning in an induction motor to like cause the back EMF to work right? So it basically is stalled at low speed. It has like no starting torque.
Very good. Yes. So flux has to be generated first, right? And when you start induction motor, the rotor is still not moving, right? And so you're still generating flux within the air gap, right? And the effect of that physically, right? The effect of that would be that the inductors, keep in mind that rotors and stators, those are just inductors, right? Windings with magnetic core. And at the beginning, since flux not yet being produced, these inductors, right, quote unquote inductors, they are acting like a short, right? Imagine you have a coil around a magnetic core, but there's no flux yet. How can you induce voltage if you don't have any flux, right? So at the beginning of when you turn on the power, right, you are connecting voltage across this inductor, right? So that at the very beginning, no flux is yet produced, so that this inductor would be acting just like a short, basically, right? And now you know why. Well, as you know, if you have a short, then you have a big current flowing, right? So that's why at starting condition of induction motor, you are dealing with, or you are going to see large current, because again, at the starting point, no flux being generated yet, the rotor is still not moving, so inductors act like a short circuit, right? That would require big current until the flux is generated, all right? And mathematically, you learn it in 295. Mathematically, this was described as a slip, right? That the resistance at the beginning of the resistance of the rotor is a function of slip, right? Does that, do you remember this? Of course you do, right? So you have slip equations, and in induction motor, slip could never be 0, right? Because induction machine is always lagging. The rotor flux is always lagging the air gap flux. Air gap flux, sorry, air gap flux. Right. Okay. Very good. You still remember. Voltage swells. What's causing it? Excuse me. Usually associated with system fault, single line to ground. So you have 3-phase line. One of the line is shorted to ground. So by KVL, right, that creates the loop, right? KVL around the loop has to be equal to 0. If this goes to 0, if this line goes to 0, then the other two have to compensate for KVL. That's why temporarily voltage on the other phases will be higher, right? Because one is grounded, okay? So if this is A, B, C, then VAB, VBC, VCA has to equal to 0, right? But what if VCA is grounded, right? Then VAB plus VBC has to compensate with the rest of the voltage, right? Basically increasing the value. Okay. That's a picture of voltage swells. And then we have voltage imbalance, defined as the maximum deviations from the average of the three-phase voltages or currents divided by the average of the three. All right, so this is just one definition. I'm going to show you different definitions. But before I do that, caused by, for example, blown fuses, right, or unequal distribution of loads. You have three-phase, right? But three-phase lines for the distribution system. But when it goes to your house, they would tap two lines, right, to make it single phase to your house, right? And then for another house, they will tap two different lines, right? And it's very hard to balance the loads, right? And for other houses, maybe they would connect. Where's the one I didn't connect yet? This way, yes, right. So let's say, you know, the first house right here is VAB, right? Connected to VAB. The second house is to VBC, and the last one is to VCA, right? How can you guarantee that all three houses will draw the same current? There's no way, right? They have their own lifestyle, right, in their house, right? Different loads in their house, right? So they will draw different currents. So it's very hard for us to balance the three-phase, right? So that's why it could give you this unbalanced event, right, under power quality. Now, I'm going to post this on Canvas. So I'm going to add this into on the future EE411 book. Let's see if I can find that page. Transients. I'm giving, you know, seminars on power quality to utility companies, PG&Es and SDG&Es. This one for SDG&E. So voltage imbalance, yeah, right here. Any deviation in voltage and or current waveform in three-phase system in terms of magnitudes or phase shift, right? There are different standards for voltage imbalance, right? I'm not going to mention those, but those are the different standards for us to be able to calculate a voltage imbalance. IEEE 1159, for example, use this equation to calculate imbalance. I think it's very important for you to know, just in case you are dealing with AC system in the future, right? The ratio of the magnitude of the negative sequence component to the magnitude of the positive sequence component expressed as a percentage. So that's the mathematical definition of percent imbalance based on IEEE standard, right? And when only RMS of line quantities are available, the above equation can be calculated as follows, right? So that equation now becomes this next equation right here, where you have beta in the equation. And beta is defined to be this equation right here. That would be in terms of line-to-line voltages, right? So that's the first definition or first equation to calculate voltage imbalance, percent imbalance. The second way to calculate percent imbalance in the system, three-phase system, is from IEEE 141, right? This is how they calculate that maximum deviation from the three phases. This is phase voltages, I believe, divided by the average value, right? Where the average value of the three phases are VA plus VB plus VC over 3, right? And then you just plug in into that equation. That's the second method. The third method is by using NEMA equations with which defines mathematically percent imbalance to be maximum deviation over average. This looks similar to the previous one, right? If you look at the previous one, is also maximum over average, but the difference is that this one from IEEE is using phase voltages, right, line to neutral, whereas NEMA is using line to line. You see that? VAB, VBC, VCA. Okay. And lastly, IEC define it to be the ratio of is it positive or negative? I think this is negative. Yeah, negative over positive sequence times 100%. Right. Okay. And I have an example right here, so I'm going to post it on Canvas, right? So you know how to calculate percent imbalance. Let's say that this is the nominal value, 120 volts, but then after you measure the voltages, you have phase voltages of 110, 119.5, 100.5. Those are the angles, and then I'm going to convert those into line-to-line voltages, right? Right there. Right, so now I have phase voltages as well as line-to-line voltages. Okay. And then I'm using all four methods. So this first method, IEEE standard 141, the way you calculate the imbalance, percent imbalance would be the average, right, of the three right there, and then divided by the maximum deviation divided by the average. So I'm finding the average first. I believe this is the second method, sorry, not the first one. This is the second method that I mentioned earlier. The average is from phase voltages, right? So these are phase voltages, right? Just magnitudes, okay? Divided by 3, that gives you 110. And then what you need to calculate is maximum deviation, right? So 110 is the average. So maximum deviation from the average. So average is 110 minus the first one is 110, that gives you 0. And then the same average value minus 119 gives you 9.5, right, for the second one. And then for the third one, 100.5. You can see that by going through that simple calculation, I know that the maximum deviation from the average is 9.5. And so the percent imbalance would be maximum deviation, 9.5 divided by the average, 110, right there. So that gives you the percent imbalance. This is the first method using the beta, right? So for the first method, you need to use line-to-line voltages right there, right, to get you beta. Then once you get beta, then you plug it into the equation that has beta in it, right there for the first method. That gives you 4.98%. Right? So as you can see, it's pretty straightforward. Using NEMA, same thing, except same as the second method, except be careful. For NEMA, we are using line-to-line voltages, not phase voltages. Right? As you can see from here, it's using VAB, VBC, VCA. So these are all magnitude of line-to-line voltages. Right? And then doing the same thing, you find the average and then find the maximum deviation of each voltage, each line voltage from the average value. And from here, you can see that the maximum deviation is 8.28 right there. Right? And so percent imbalance would be maximum deviation 8.28 divided by the average 190.64 times 100%. Okay. This last one, don't worry if you haven't taken 406, 407, you probably don't know what sequence, how do you calculate sequence from phase quantities, right? So don't worry about this if you have not taken 406, 407, but it is still good to know that IEC is calculating the three-phase percent imbalance based on sequence components instead of phase components. Okay, right? So those are the 4 different ways to calculate percent imbalance, and you see the equation to convert from phase quantities to sequence components right there. Right. Again, don't worry if you haven't taken 406, 407 yet. All right, so that's percent imbalance. Any questions on these?
I had a question.
Yeah.
Are these variations pretty standard? Like the voltage variations you put in these example problems, are these fairly standard for what a house would see?
I don't know what standard is. I think there's a limit for percent imbalance. Oh, I don't know what that limit is. Maybe it's in here. Yeah, it should be in here. Yeah, right here. For example, the limits should be less than 2% during 95% of each period for 1 week, right? So I don't know if there's any standard, but I think limit, there should be a limit, right? This is an example of the limit that we have for percent imbalance, less than 2% during 95% of each period for 1 week.
Okay. I'm assuming that can affect the power electronics you use when knowing what to take in. You're not always going to have 120 RMS. You're going to have a little variation.
Absolutely, yes. If you, I don't know if you're familiar with the IT curve for power supply. I don't know what they call it these days, but IT curve is a curve that you have to look at when designing offline power supply. Offline power supply means what? A power supply that is connected to the wall plug, basically, right? AC input, right? And with this curve, I don't have it here, but you can Google it, ITIC. I think they have different names these days. You'll see that there is a range that you have to follow with IT curve. The x-axis, I believe, is voltage level. The x-axis is the time. So depending on the duration of the time, how much voltage beyond the nominal value should be acceptable by switching mode power supply or offline power supply, period. So definitely, percent imbalance would affect that, IT curve, something that you have to consider if you are designing offline power supplies. That's another reason why I think this is important for you. This topic right here is very important for you, because most maybe in the future you'll be designing, offline power supply. Right?
Is that primarily caused by your neighbors taking different amounts of current or total power than you, like steady state wise?
It's not just how much power. I mean, I think if the neighbor is taking power, as long as the power is clean, it's fine. It's just going to be, maybe a little bit of a sag, and then your electrical system will react to it to improve the voltage. But then the problem is when the neighbor is running some, heavy power electronics equipment that would distort the power, basically, right? And that could be a problem with the RMS value. I'll explain later, maybe not today, on Thursday, that when you have harmonics in the system due to power electronics, for example, then it's going to be different for you to calculate RMS, right? The RMS that you're getting could be higher, right, than the nominal value because of harmonics, right? So that's a problem, right? When you compare that to the IT curve, for example, that strictly defines voltage level acceptable by offline power supply. So again, it's not just how much power, but also the quality of the power. Does that make sense?
Yeah, thank you.
Waveform distortion, that could be in the form of DC offset, harmonics, interharmonics, notching. DC offset is probably one of the worst thing too. So electrical system, AC systems should not have any DC offset, right? But if it does, then we got a problem, right? Because then if it goes into the transformer, for example, that's going to drive the transformer higher into saturation region, right? Imagine BH curve. Right? BH curve looks like this, right? The hysteresis curve, basically, that looks like this, right? So if you have a 60 hertz component, no offset, supposedly, right, it will basically, depending on the current, it will go through this cycle, positive cycle, negative cycle in the core of the transformer. I'm drawing the BH curve of the core of the transformer. So the flux goes up and down, goes up and down. But if it sees a DC offset, when it goes up, it will go up higher, right? Higher, but then it's the same voltage, so it's going to go down less for the same amount of fluctuation in the voltage, right? And then when it when it goes positive again, when it sees DC offset, it will go higher again. And then the same amount of fluctuation the other way, right? So then eventually it will go to saturation like that. Then before you know it, the transformer gets so hot, and you'll probably see fire in the transformer if it's a big transformer, right? It gets so hot because of that. Okay, so DC offset is dangerous. Yeah, you don't want to have that in the AC system. Harmonics, that's a big one for power electronics. Interharmonics, that's a different type of harmonics. We'll talk about it later. Line notching, that's the one that can cause zero crossing, more than two zero crossing in one period of a sine wave. And then we have the general noise coming out of waveform distortion, right? So I've already talked about DC offset, the cause of it mainly from half-wave rectifier. You learn it in EE411, right? If you have a half-wave rectifier that looks like this, right? Simple half-wave rectifier like that, right? This is your AC input. Then the current, right? Here's the AC side right here, right? The AC side will have to supply this type of current, right? Half-wave, this is the zero, right? That means it has a DC offset. The average of this is a DC offset. And this current comes from a transformer, comes from the distribution transformer. Right? So imagine if this current comes from here, right? But luckily, transformer is blind to DC, right? So it will shift that down to that kind of current there on the primary side. But nevertheless, this DC offset, when it gets so high, it could be damaging to this transformer, right? But on the primary side, it's safe because, again, inductor is blind to DC, right? It's just going to be a short to a DC. Okay. Let's see what else. Harmonics, sinusoidal voltages or currents having frequency that are integer multiples of the fundamental frequency. That's the definition of harmonics. The key word there is integer, right? So sinusoidal voltages or currents having frequencies that are integer multiples of the fundamental frequency. What is fundamental frequency? That's the operating frequency of the system, right? In our country, is 60 hertz mainly. In other electrical systems, such as submarine, for example, spacecraft, maybe aircraft, I should say, not spacecraft, but aircraft, that could be higher, could be 400 hertz. Right? So whatever the operating frequency of the generator, that would constitute the fundamental frequency. So harmonics will be integer multiples of that frequency. Originated from the nonlinear characteristics of devices and loads on the power system, such as those found in power electronics devices. And then there's a standard or guideline, I should say. So if you go to the standard, it gives you guidelines on harmonic level that you should have for different level of electrical systems, right? Voltage-wise, right? So electrical system can come from different voltage levels. So depending on the voltage levels in the AC electrical system, that will determine the limit for the harmonic present, the presence of harmonics, right? Based on different level of voltages. Yeah. Here's an example that you've seen, that you saw in EE411. I don't know if you remember this, but this is the current that is being drawn from where? Do you remember this? Oh, you probably already have it here. Oh yeah, from three-phase rectifier. So if you have a three-phase rectifier, right, three-phase AC, three-phase bridge rectifier, that's the current that you'll be seeing, right, at the input of the rectifier on the AC side. And this gets worse when the load is capacitive, right? So if you have three-phase rectifier that looks like this, right? Bridge rectifier. And phase A, phase B, and phase C, right? That's the three-phase. There's the current. One of the line current looks like that. And that happens when you have resistive load. If you add capacitor, which you will, because you want to get a flatter DC, right? You want the DC to be more flat. So the customer is good. The customer is happy because it's seeing, you know, a better DC because of the cap. But the cost of that would be the input current will look even uglier than this, right? It will look something like this with a gap, like discontinuous current. Right? That's even more harmonics. So these harmonics becomes bigger, basically, because of that. Right? Okay, so keep that in mind if you ever designing power electronics from three-phase with three-phase bridge rectifier. As soon as you connect a capacitor, then the input current will get worse in terms of the quality of the sine wave, right? And this is the harmonics, right? This is time domain. The top one is time domain waveform of the current. The bottom one is the FFT, so the frequency content of the current. The first one is the fundamental component right there. That's the 60 hertz. But look at the noise right there, right? And this noise gets bigger, much bigger if you have capacitor. Okay. Interharmonics are voltages or currents having frequency components that are not integer multiples, right? So integer multiples means 2 times, 3 times, 4 times, right? Are there such a thing as, you know, harmonic noise at 1.5 maybe times the fundamental component? The answer is yes. So between the harmonic of the power frequency voltage and current for the frequency can be observed, which are not integer multiples of the fundamental component. They can appear as discrete frequency or as a wideband spectrum, right? So main sources of these are static frequency converters, right? Cycloconverters, induction motors, and arcing devices. Oops, sorry. It's known to affect power line carrier signaling and to induce visual flicker in display devices such as CRTs and heating. So yeah, it is possible to have harmonics that are not integer multiples. Those are called interharmonics. Notching is a problem that we have on the voltage into the three-phase rectifier. So the same three-phase rectifier I drew earlier, right? 1, 2, 3, right? So you have 1, 2, 3 again. Earlier you saw the problem with the current, right? So here's A, B, and C, right? Here's the load. Right? So voltage ideally is going to be sine wave, right? Voltage input ideally will be sine wave. But the thing is, as you learn from this class as well as EE411, mainly this class, diode takes longer to turn off, right? So therefore, and as you know, for each leg, right, you have phase A leg, right, B and C. For each leg, the 2 diodes cannot be on at the same time, right? They cannot be on at the same time. Otherwise, you're going to have a short across the source. So therefore, right, it could happen, right? If, for example, the top diode is supposed to be off, right, and the bottom diode is supposed to be on. The top diode is off, is turning off, but it's turning off slowly. That it is still on, right? And then the bottom diode is supposed to be on, but it's turned on real fast, right? So the on time of the diode is turn on time of the diode is much faster than the turn off. So you can see that it is possible for the two to conduct at the same time. That's how you see this voltage pull to the ground, right? That's called notching. And you can see there's 6 of them per one cycle. If you focus on the black waveform right there, you can see there's 1, 2, 3, 4. Can see. No, is it 4? Yeah, that's 4. Doesn't make sense. I have more than 6. It's not the peak, sorry, this is not part of it. That's something else. I don't know what that is. So it should be 1, 2, 3, 4, 5, and 6. Yes. Yep. So it'll be 6 notching per period. That's corresponding to the 6 diodes, right? And as we learned from E410, the commutation does not occur on the peak on the peak part of the voltage. Yeah, I'm not sure why we have those. Anyhow, those are line notching. That's what could create additional zero crossing. If it dips down far, right, and it goes to 0 volts, then yeah, any controller that relies on zero crossing will get confused because of that. And then we have noise, defined as unwanted electrical signals with broadband spectral content lower than 200 kilohertz, superimposed upon the power system voltage or current in phase conductors, or found on neutral conductors or signal lines, caused by power electronic devices such as rectifiers and switching power supplies, will disturb sensitive electronic devices such as microcontroller or PLCs. I talked about PLCs before. Okay, and then we have power frequency variations, often referred to as flicker. It's defined to be systematic variations of the voltage envelope or a series of random voltage changes, the magnitude of which does not normally exceed the voltage ranges of 0.9 to 1.1. So it's still within the normal range, right? Between 0.9, between 90% to 110%. Right? So voltage level wise, it's still okay. But the thing is, you know, it has this lower voltage fluctuation, right? Lower than 60 hertz. Right? So to the point that our eyes can actually see the fluctuations, right? Slow enough for our eyes to see. Right? I think I mentioned this. I don't know if it is this class or the other class that I ran this experiment in the lab, and I found out that my eyes can see flickers down to what is it, 35 hertz, I believe. Right. So yeah, we could see flickers, or at least to me, I could see flickers for any frequency lower than 35 hertz. All right, any questions so far? So I kind of went briefly on the different definitions of power quality events. So we're gonna focus on harmonics after this. No questions? All right. What are harmonics? Right, so comprises of sinusoidal voltages or currents having frequency that are integer multiples, right, as I mentioned earlier. What is fundamental frequency? This is typically the nominal operating frequency of our system, electrical systems. Could be 50 hertz, 60 hertz, 400 hertz, what have you. The fundamental frequency is the first integral component of harmonics. So harmonic number 1, that will be our nominal operating frequency. Right? So if we are operating 60 hertz electrical system, 60 hertz electrical system, then the first harmonic will be at 60 hertz. Right, and then harmonic analysis entails analyzing a periodic waveform by breaking it down into a bunch of sinusoidal waveforms at various frequency, you know, series of sinusoidal waveform at various frequency, which is what we know as Fourier series. If the fundamental frequency is 60 hertz, then its harmonics will be located at integer multiples of 60 hertz. For example, first harmonic is the 60 hertz itself, fundamental frequency. Second harmonic will be 2 times 60. Third harmonic will be 3 times 60, right? Or graphically, if I draw with respect to time, fundamental component is 60 hertz, then second harmonics will be faster, right? Twice as fast as the fundamental component. And third harmonics will be 3 times as fast as the fundamental component, right? But each of these are sine waves, okay? Don't forget, each one of these harmonic component, right, corresponds to a sine wave at the harmonic frequency. So then a pure sinusoidal waveform should have one harmonic component, which is at its fundamental frequency, right? If you have a clean, ideal sine wave like this, right? This is time domain. If you convert it into, or if you look at the frequency domain of this, you should only see one component right there, right? At 60 hertz, for example. So that's at fundamental component. Right? But then if you have non-sinusoidal waveforms such as this, then right away you should expect to see frequency components that are more than just the fundamental component. So I can see the fundamental component right there from here to here. That's the period, fundamental period. So the inverse of that gives you the fundamental frequency. But in addition to that, I also have other AC components, right? As you can see from the fluctuations. So if you take FFT of that, look at the frequency content of that waveform, sure enough, we have more than just fundamental component. Fundamental component, third harmonics, fifth harmonics, right? And so on and so forth, right? And the reverse process would be also true, right? If I could break down a periodic waveform into its frequency content, I could also construct, right, bunch of series of sinusoidals at different frequency, construct from those frequencies a periodic waveform, right? So the reverse process basically. So here's an example where I have 3 sinusoidals, see that? The first one is 60 Hertz, second one is 3 times 60, the third one is 5 times 60, and I'm just adding them up, see that? I'm adding all of these sinusoidals, and I take a look at the output. So I should be able to construct a periodic waveform, see that? Exactly the same as I had in the previous example, right? Triangular waveform, right? It looks like a sine wave, but it's not quite, right? You can see that it is trying to mimic a sine wave, but it's not quite. So therefore, I know that we're going to have frequency components other than the 60 Hertz. So that's the first one, 60 Hertz, and then the fundamental components right there, right? Okay. And if you are wondering why there's only odd numbers, there's no even numbers, that has to do with the symmetrical property of this waveform, right? This is called odd symmetrical waveform, right? Where the positive cycle is the same as the negative cycle.
Professor?
Yeah.
Why do these harmonics negatively affect the supply line? Like, in what way do they?
That's going to be next.
Okay, okay.
We'll talk about the effects for the conductors, right? There are many effects. That's why it's important for us to, I believe, to go over this chapter, right? So hopefully on Thursday we'll go over that. Okay. And then a square wave, same thing, right? You have these harmonic contents, right? And because of the symmetrical property again, the even numbered harmonics are gone or disappear. You only have the odd harmonics, right? I don't know if you remember Fourier series. I think I have it maybe next. You have cosine and sine terms, right? So depending on the symmetrical property of the waveforms, you can only have cosine or sine or both, right? But for that kind of symmetrical, what do you call it? I think odd symmetrical, right? Property, only the sine functions appear in the Fourier series. And here is input current that you will be seeing if you are designing a single phase rectifier into your offline power supply, right? So single phase from the wall plug, right? If you just have rectifier and capacitor, nothing else, and that's the kind of input current you expect to see, right? Ugly waveform is not even sine wave, right? Has gaps. That's even worse, right? So if you look at the harmonics, then you get all of these harmonics in the line, right? You've seen this one before from adjustable speed drives, right? And the content is 6K plus minus 1, right? So you got 1, 5, 7, 9, 11, and so on and so forth. Or 11, 13, sorry. 1, 5, 7, 11, 13, and so on and so forth. So to summarize, a pure sinusoidal waveform plus a waveform or more at multiples of its frequency results in a distorted waveform that is said to contain harmonics. So good, and then high frequency is bad, and then you get, you know, some, I don't know, funky looking, you know, waveform that could be bad to the system, right? Here's the mathematical representation. I'm just going to go through this briefly because you covered this in 228. Right? Any periodic waveform could be expressed in terms of Fourier series. Right? You have the constant value that represents the DC offset of a waveform. And then you have the cosine function and the sine function, right? With all the coefficients A1, B1, right? And then depending on the symmetrical property of the waveform, that would determine whether or not you have only the sine portion of the Fourier series or cosine or both, right? Yeah, symmetrical waveform, one in which the yeah, there you go. So if you have a symmetrical waveform, right, then it will produce odd harmonics. If it's asymmetrical, then it will produce even harmonics, right? So these are examples of symmetrical waveform, right? And here's the example of asymmetrical waveform, right? In our elliptical systems, which one is most commonly found? I would say symmetrical waveforms. Why is that? Well, because our electrical system is based on sine wave, right? So any electrical systems that we are designing or we are using would have to be able to interface with a sine wave system, right? So therefore, anything that we are any AC that we are generating from our electronics, for example, has to mimic a sine wave, right? So a sine wave is a symmetrical waveform, or the output that we get from the electrical system that will be derived from a sine wave. That's also why symmetrical waveform is common in our electrical systems. Okay, and then based on the Fourier series, depending on how many sine waves you include in the series, that would determine how well the shape of the waveform that you want to produce, right? For example, if I want to create a triangular waveform, right? I'm only using one sine wave in the Fourier series. Look at that, it's only one sine wave, right? Then of course what you'll be seeing is sine wave, right? This is one I want to achieve, a triangular waveform. But if you only use one sine wave, then of course you'll end up with a sine wave waveform instead of triangular waveform. But if you add more sine waves, say 5 of them, you can see that I have a better approximation of better waveform, right? Better match to a triangular wave. See that? So now I'm adding 5 sine waves in the Fourier series. Look at the resulting waveform. Right? Now it's looking more like a triangular wave. What happens if I include 100 sine waves in the Fourier series? Then you get even better triangular waveform. See that? Okay. So I can use, like I said, like I had before, I can just simulate this, right? With I don't know how many sine wave, 1, 2, 3, 4, 5, 6, 7, 8, to create a triangular. Actually, this is rectangular wave, right? At different stages. I don't know how many is this one. This is n equals to 3. So that's the square wave that you're getting. N equals to, I don't know what that is, 4. Yeah, 4. You got better square wave. 8, even better, right? Square wave. All right. Okay.